Welcome to BackToCoding. I am Milind Amrutkar and today I am going to show you the technique that will transform how you solve array and string problems, the sliding window technique. This single concept can reduce your solution from O of n square to O of n, making your code lightning fast. So grab your coffee and let's dive in. Imagine you are looking through a window of a moving train. As the train moves, you see different scenery through that same window frame, right? That's exactly how the sliding window technique works. The sliding window technique is like having a window or a frame that slides across your data, whether it's an array or a string. Instead of checking every possible combination, we smartly move our window and keep track of what we see. Think of it like this: instead of taking 100 separate photos of a landscape, you record a video while slowly panning your camera. Much more efficient, right? Where is it used? Finding maximum sum of k consecutive elements, longest substring problems, finding patterns in strings, anytime you need to examine chunks of data. Now you might be wondering why use it. Well, it's simple. It converts nested loops into single loop, dramatically improving performance from O of n square to O of n. That's the difference between your code running in 1 second versus 1 hour on large datasets. Let's understand this with a real problem. Say we have an array of daily temperatures and we want to find the maximum sum of any 3 consecutive days. When I say consecutive, I mean elements that are next to each other in the array, like neighbors in a row. Here's how most beginners would solve it the brute force way. Let me show you what's happening here with our array and k equals 3. Let's dry run it. When I equals 0 and we calculate sum of 2 and 3, we get 6. When I equals 1 and we calculate sum of 1, 3, 4, then the sum is 8. When I is 2, calculate sum of 3, 4, 1, we get 8. When I is 3, calculate sum of 4, 1, 2, we get 7. When I is 4, calculate sum of 1, 2, 1, we get 4. When I equals 5, calculate sum of 2, 1, 8, we get 11. So we get maximum sum as 11. The problem here is that we are recalculating the same elements over and over. When we move from 2 and 3 to 1, 3, 4, we are calculating 1 and 3 again. That's wasteful. Here the time complexity is O of n times k, where n is the array length and k is the window size, and space complexity is O of 1. Why is this O of n times k? Let me break this down step by step. The outer loop runs n minus k plus 1 times. Let's use our example. Here array length is n equals 8 and window size is k equals 3. The question here to ask is how many different starting positions can we have for our window? Let's see them. We can have position 0. Here window covers indices 0, 1, 2. Their values are 2, 1, 3. For position 1, window covers indices 1, 2, 3. Their values are 1, 3, 4. For position 2, window covers indices 2, 3, 4 and values are 3, 4, 1, and so on until we are at position 6. So for position 6, window covers indices 6, 7, 8, but here index 8 doesn't exist. So hence we have count as 6 valid starting positions, which is 8 minus 3 plus 1 and is nothing but n minus k plus 1, where n was array length, which was 8, and window size, which is k, was 3. And our inner loop runs k times for each outer loop iterations. For each starting position, we need to calculate the sum of k elements. Position 0, sum is array of 0 plus array of 1 plus array of 2 equals 3 additions. Position 1, sum equals array of 1 plus 2 plus 3, 3 additions, and so on until position 5, where sum equals array of 5 plus array of 6 plus array of 7, which is again 3 additions. Each position requires k equals 3 additions. So the total operations are number of starting positions multiplied by operations per position. Formula is number of starting positions times operations per position. So it's n minus k plus 1 times k, which in our case is 6 times 3, which is 18 addition operations. So hence the time complexity is O of n times k, where n is array length and k is window size. And space complexity is O of 1, which is constant space. No matter how big our input gets, we use the same amount of extra memory. Now let me blow your mind with the sliding window approach. Instead of recalculating everything, we'll be smart about it. The strategy is to calculate sum of first window, then slide the window, remove the leftmost element and add the new rightmost element, and keep track of maximum sum. It's like sliding a frame across our array. Here's the code using sliding window technique. Alright, this is where the magic happens. Let me show you exactly how our sliding window moves through the array. I want you to follow along and see how we are being super smart about reusing calculations. Our array was 2 1 3 4 1 2 1 8 and positions are 0 1 2 3 4 5 6 7. Step 1 is initialization, which is setting up our first window. So let's start by calculating our very first window of size 3. Window is 2 1 3 and positions are 0 1 2. Window sum is 2 plus 1 plus 3, which is 6. Maximum sum is 6. This is our best so far. Think of this as placing our window frame over the first 3 elements. Step 2. The sliding begins. Here's where it gets exciting. Slide 1. I equals 3, moving our window 1 position to the right. Current window was 2 1 3. Now it becomes 1 3 4. What do? Instead of adding 1 plus 3 plus 4 from scratch, we are clever. We remove the left element, which was array of 0 equals 2, and add the new right element, which is array of 3 equals 4. So window sum is 6 minus 2 plus 4, which is 8. Our window now is 1 3 4. Maximum sum equals max of 6, 8, which is 8, our new champion. Here 6 was our previous max sum. Slide 2, I equals 4. Window shifts from 1 3 4 to 3 4 1. We remove array of 1 equals 1 and add array of 4 equals 1. So window sum is 8 minus 1 plus 1, which is 8 for window 3 4 1. Maximum sum equals max sum of 8, 8, so it's 8 again. Slide 3, I equals 5, window shifts from 3 4 1 to 4 1 2. We remove array of 2 equals 3 and add array of 5 equals 2. So window sum is 8 minus 3 plus 2, which is 7 for window 4 1 2. Max sum equals maximum sum of 8, 7, which is 8. Not good enough to beat our existing champion. Slide 4 is I equals 6. Window shifts from 4 1 2 to 1 2 1. We remove array of 3, which was 4, and add array of 6, which is 1. Window sum is 7 minus 4 plus 1, which is 4 for the window of 1 2 1. And max sum is maximum of 8, 4, which is 8. Nope, still not beating our record. Slide 5, I equals 7. Final slide. Window shifts from 1 to 1 to 2 1 8. We remove array of 4, which was 1, and add array of 7, which is 8. The window sum is now 4 minus 1 plus 8, which is 11 for window of 2 1 8. Maximum sum equals maximum of 8, 11, which is 11, and we have got a new champion. So final result is maximum sum equals 11 from the window 2 1 8. See how beautiful that was. We only did 5 additions and 5 subtractions instead of calculating 18 separate additions like the brute force method. That's the power of sliding window. We reuse our previous calculations. Time complexity for this approach is O of n since it's a single pass through the array, and space complexity is O of 1 since we are only using a few variables. Alright team, this is where we put on our performance analyst hats and see exactly why sliding window is absolutely crushing the brute force approach. Get ready for some mind-blowing numbers. For brute force approach, time complexity was O of n times k. Remember our outer loop? It runs n minus k plus 1 times. That's how many starting positions we have. For each of those positions, our inner loop runs k times to calculate the sum. So we are doing n minus k plus 1 times k operations. For large arrays, n minus k plus 1 is basically n, so we get n times k operations. That's a lot of repeated work. Space complexity was O of 1. We are only using a handful of variables: maximum sum, current sum, I, j. Doesn't matter if our array has 10 elements or 10 million. Same memory usage. For sliding window approach, time complexity was O of n. First we calculate our initial window sum, that's k additions, O of k. Then we slide through the remaining positions, that's n minus k slides, which is O of n minus k. Each slide is just one subtraction and one addition, super efficient. Total operations are O of k plus O of n minus k, which is nothing but O of n. We have eliminated all that redundant calculation. Space complexity is O of 1, same story, just a few variables. Memory usage stays constant regardless of input size. Let me blow your mind with a concrete example. Say we have an e-commerce website analyzing daily sales data. So scenario is 10,000 days of sales data, looking for the best 100-day period. In the case of brute force, operations are 10,000 times 100, which is 10 lakhs or 1 million calculations. And if each operation takes 1 nanosecond, it's 1 millisecond in total. Now, for sliding window, operations are 10,000 calculations, just one pass. And if each operation takes 1 nanosecond, then it's 0.01 milliseconds in total. The result is 100 times faster. But wait, it gets even crazier with bigger datasets. Brute force is 1 million times 1000, which is 1 billion operations, and for sliding window it's 10 lakhs operations or 1 million operations. That's 1000 times faster. This is the difference between your algorithm finishing in 1 second versus 16 minutes. In production systems, this could be a difference between real-time responses and users abandoning your app. So the bottom line is sliding window doesn't just make your code faster, it makes impossible problems possible. Here's your cheat sheet for recognizing sliding window problems. Think of two buckets, fixed window and variable window. For a fixed window, window size is given as k. Examples you will see are maximum minimum sum of k consecutive elements, average of sub-arrays of size k, contains duplicate within k distance. If the challenge hands you a number k and says consecutive, that's your cue. Variable window. Window grows and shrinks based on a rule. Classic ones are longest substring without repeating characters, smallest subarray with sum greater than equal to target, longest subarray with at most k distinct elements. Here we adjust the window until a condition is met, then tighten it. Note that a subarray is a contiguous part of an array, like taking a slice. A substring is the same concept but for strings, a sequence of consecutive characters. Alright, before we wrap this up, let me share some pro tips that will make you a sliding window ninja. Let's see them. First, always watch out for the edge cases. What if the array length is smaller than the window size? What if the window size is 0 or even negative? These little details can break your solution if you don't think about them first. So step 1, handle edge cases like a pro. Second, remember there are two main flavors of sliding window. Fixed size, the window length stays constant, like find the maximum sum of k consecutive elements, and variable size, the window grows or shrinks based on conditions like longest substring without repeating characters. Given this distinction right, and half your confusion is gone. Third, know the common tools used inside sliding window problems. Use a hash map when you need to track character or element frequencies. Use two pointers for variable size windows where the one pointer expands and the other shrinks. And if you are looking for max or minimum inside a window, a dequeue is your best friend. If you remember these patterns, most challenges will start looking familiar. And finally, practice, practice, practice. Don't just stick to one kind of challenge. Try sliding window with condition checks, sliding window with multiple constraints, sliding window on strings with character frequency tracking. The more variations you solve, the stronger your pattern recognition becomes. And there you have it, world-class coders. You just mastered the sliding window technique that can solve dozens of coding interview challenges. Remember, the key is to think, can I reuse computations as I slide my window? If this video helped you understand sliding window, smash that like button, subscribe to BackToCoding for more coding gems, and drop a comment telling me which technique you want to learn next. Until next time, keep coding like the champion you already are, and keep watching BackToCoding.